Hi, this is Peter with CalcBook, and today we're going to be looking at concrete spread footings. So let's do a quick recap of spread footings, right? They're typically found beneath columns, and they are designed to resist vertical, lateral, and overturning forces. We can see there in the diagram. And when we check spread footings, we check for both stability things and strength things. So for stability checks, right, we're going to look at bearing pressure, sliding, and then overturning of the foundation. And then for strength checks, right, we're going to check one-way shear, two-way shear, which is also known as punching shear, and then bending. So our flexural reinforcement design. So in CalcBook, right, we right now we have single axis bending only, and are working on biaxial bending, which will be coming out soon. So let's take a look at our problem statement for today. Right, we're going to be designing this foundation in accordance with ACI 318.19. We've got a footing depth of 2 feet. We've got a depth of soil above the footing of 2 feet. Our pedestal is going to be an 18-inch square pedestal. The height of the pedestal is 3 feet, so you can see it's sticking above the soil about 1 foot. Our footing is going to start out at 10 feet square. We've got number 9s at 12 inches as our flexural reinforcement. We've got an F prime C of 4,000 psi. Our steel reinforcement yielding is 60,000 psi. And our allowable bearing capacity for dead plus live is 3,000 PSF, and we are permitted with a 1/3 increase for total, so for earthquake or wind loading. That'll give us a allowable bearing, a total allowable bearing of 4,000 PSF. And our loading there in the bottom right corner, right, we've got an applied vertical dead load of 180 kips. We've got an applied vertical live load of 120 kips. A lateral shear at the top of the pedestal of 25 kips due to earthquake, and then a moment at the top of the pedestal there applied of 350 kip foot. So let's go ahead and open up CalcBook and we'll get started on the design. All right, I've got CalcBook open now, and we're going to click into our concrete design module here. So the ACI 318-19. Go ahead and click into our standalone designs and then click into our spread footing designs. This is a module that we're really excited about here at CalcBook. It's a design module that not a lot of other programs have. The level of detail that we do, explaining all the different options and how the footing is designed when it comes to overturning and eccentricities and that sort of thing. And we'll dive into all of that. So we're pretty excited about this module, and we hope you guys check it out. So typical layout here, we've got our inputs on the left side, so we'll start clicking through these options here. We are going to include our footing and pedestal weight. We're going to include the vertical soil weight because we have soil above the footing. We are going to include sliding and overturning. And then we have an option here for whether or not our lateral loads are due to seismic or wind. And this has to do with increasing the permitted lateral soil pressures. So we want to go ahead and keep this as yes, because our loads, our shear and moment is from earthquake loading. And then we've got an option here to select whether or not we want to include the top 1 foot of the soil. So typically, if you don't have a slab or some other rigid member above the soil, you cannot include the top foot of the soil for lateral resistance. So we are going to assume this is nothing on top here. So we are going to exclude that top foot. So we're going to leave this as no, which is the default. And then for our sliding resistance, we are going to use friction. You can option for cohesion, which is another option in the IBC tables for lateral sliding resistance, but we're going to go ahead and use friction. Okay, so let's go ahead and enter in our footing dimensions, right? We have a 10-foot square footing. Our footing thickness is 2 feet, and our depth of soil is 2 feet also. Our pedestal is going to be 18 inches, so 1.5 feet in each direction. Our height of pedestal is going to be 3. And as soon as we started entering the pedestal information, we got a pop-up here for the column location factor. We're going to leave that as an interior column. Then we need to enter in our rebar information, right? So we have number 9s at 12 inches. So we have to do a little bit of math here. Since we have a 10-foot square footing, we're just going to assume that's going to be 11 bars. All right, so that's it. We have all of our information loaded now for the capacity side. There's a lot of default values here that we can run through. The one thing we do need to change is our allowable bearing pressure. So we're going to go ahead and change this to 3,000 for our dead plus live. And then it's going to give us a warning here letting us know that the total bearing pressure right, for earthquake or wind has to be at least what we put in for dead and live. So we're going to update this to 4 KSF, right, because we had a 1/3 increase. And then there's some other items in here which I don't think we need to update. Talking about our soil weight, sliding coefficient of friction, which we're pulling this from the IBC tabulated values. Our factor of safety against sliding and overturning, which you can adjust if you want. And then we have our concrete properties and our steel reinforcement properties, which we're going to leave as is. All right, so now we've got our capacity side entered. We're going to go ahead and enter in our demands. So we are going to start with, let's see here, we've got our axial demand dead load of 180 kips, live load of 120 kips. We've got a moment demand due to earthquake of 350 kips, and then a shear demand due to earthquake of, let's see here, 25 kips. Okay. We can see right away, right, we've got our design is not okay due to the bearing pressure. So let's go ahead and start digging into this and we can figure out what we want to change before we check our strength calculations. So we've got a few things here under the demand section because we've got quite a few different types of demands for footing design. So the first thing is going to be adding in our supplemental loading. So our footing weight, our soil weight, and our pedestal weight are all included. So that all gets applied to our 180 kip applied dead load. So our total dead load for this is 234 kips. And then if we open up one of these demands here, we've got quite a few different load combinations, right? And that's for each different type of failure mode or check that we're doing. So we have one, right? We have ASD loading for the total bearing load. We have ASD loading for the dead plus live. And you can see this is 0, right? Because we don't have any moment demand for dead and live. And then we have some various other ones here for our LRFD, for flexure, and for one-way shear and two-way shear, right? And you're going to get that under each different load case. So for axial, right, you have all these again, and then same thing for your shear demand. So getting into bearing pressure, right, that's our controlling limit or limiting design factor right now. First thing we need to do is check our eccentricity, right? So we're going to take our applied moment that we have, 183 kip foot, and then we need to add in our shear, right? Because our shear is applied at the top of the pedestal and we're determining our eccentricity at the base of the foundation, we need to take this shear, multiply it by our height of our pedestal plus our height of our footing to get that extra moment. So we have our shear times the depth of the footing plus the height of the pedestal. That gets our total moment, right? We can figure out what our current area distance is, that L over 6, and what our eccentricity is, so our M total over axial. So it gives us an eccentricity of 0.77 feet. And that is within the current area. So we do have some eccentricity, but it is still within the current area. So that means our foundation is completely in contact with the soil, right? So we get a distribution kind of like this. Right, then we can calculate our maximum and minimum bearing pressure, right? This is based off of, that P over A plus M over S equation. It's manipulated a little bit to account for the eccentricity in terms of, E and L and that sort of thing. But we get 4.74 KSF, right? And our allowable is 4 KSF. So we get a DC ratio of 1.2 for our bearing pressure. And if we were to look into, for instance, just the dead plus live, we would be doing the same thing. But there's obviously no eccentricity for dead plus live, right? So we just have that P over A for our bearing pressure here, which is also over its capacity, but the total gives a higher DC ratio. So that's why you're seeing that one here. So before we go into the rest of the design, let's go ahead and get this bearing pressure sorted out so that our strength design calculations, we won't have to redo those again. So we're just going to go ahead and start by increasing the size of the foundation to reduce that bearing pressure. So if we go up a foot, right, that's 1.01. So we're almost there. So we'll just go up one more foot. So we've got a 12 foot by 12 foot foundation. That gives us a 0.96. Now switching over to the two-way shear demand. So that's the controlling factor now. But that's okay for now since we're less than 1.0. And the only thing we're going to update here, since we increased our foundation size, we're just going to add a couple bars, our flexural reinforcement, to make sure we stay at that 12 inches on center. Okay, so now that we've done that, we can see that we are below now 3.28 KSF. We're below our maximum bearing pressure. So we can keep going through our checks. So now we can go into our flexural demand, right? This is going to be using LRFD loading. So it goes back through and calculates the overturning moment in accordance with the LRFD load combinations, recalculates our eccentricity, And then it determines what our bearing pressures are, right? These are our ultimate bearing pressures now because we're using our LRFD load combination. So these are actually not used against the allowable bearing pressure. It's only used to determine the strength calculation. So for moment in this case, right? And then we want to figure out what our bearing pressure is at the face of the column, right? Our critical section for bending is going to be here at the face of the column. So we want to figure out what this Q face value is. We figure that at 3.19 KSF. Then we can go from there and we can figure out what our basically the total force acting on this edge of the foundation here, pushing upwards on the foundation, which is going to cause that bending. So we get our force F1 of this rectangle, the moment arm X1, and then we calculate this triangle here, F2, and then its location, X2. And then we can get our total demand at the face of the column of 686 kip feet. So now moving on to the shear demand, right? We need to figure out what our depth to reinforcement is, what our distance is from the end of the footing to the face of the pedestal. Then we want to figure out what our bearing pressure is at D away from the face, right? That's where the critical section is for one-way shear. So we want to figure out from D away from the face what that Q shear value is going to be. We figure that at 3.66 KSF. And then we can figure out what our total area or our total loading is there from the bottom of the foundation pushing up to figure out what our load on that critical section is for one-way shear, which comes out to 176 kips of force. Then we can move on to our two-way shear demand, right? So we again recalculate our eccentricity. For this, the critical actually does not include any overturning. It's going to be our pure vertical loads. So then we calculate based on that D over 2 away from the face, right? We have our 45-degree failure plane for two-way shear, but we calculate the shear plane, the shear area at D over 2. So that's where we figure out these areas on each side, basically around the perimeter of the foundation. And that gives us a two-way shear demand of 466 kips. All right, so now we can take a look at the capacity side of things. So we're going to start with our sliding capacity. And right, the first thing we're going to do is figure out what our actual depth of soil is to the bottom of the footing based on excluding that top 1 foot. So we have our soil and our footing depth and then minus 1 foot. Right, then we're going to figure out what our earth pressure is at the top of the footing. So figuring out right at this top of footing here, we're going to ignore any pressure against the pedestal, right, just against the foundation. So we are excluding that 1 foot. We figure out what our pressure is at the top of the footing, figure out what our pressure is at the bottom of the footing, right? And then we have this diagram here for what our actual sliding resistance is due to the passive pressure. And then we can add in our frictional resistance, right? So this is just our dead load or our vertical loading times the coefficient of friction of 0.35. And then we can add the two together, get a total sliding resistance of 57.44 kips. And then we can figure out what our factor of safety is, right? So this is the true factor of safety here, just our demand over our resistance. And our resistance over our demand gives us that factor of safety. And it's important to note that, in the output window, if this was controlling, it would already include the 1.5 factor of safety we have against sliding. But here it's reporting the true factor of safety. Okay, then we can check our overturning capacity. So first thing we want to do is just confirm our total overturning moment, right? Which is going to be this 332 kip foot. Then whatever our resisting moment is, right? So our dead load times half the distance or half the width of the footing. And then we have a 2.8 factor of safety against overturning, so we're good there. Next, we want to calculate our flexural capacity. I'm not going to get too deep into this. We have other videos on our concrete design sections, and this should all look pretty familiar. It references all the same steps to calculate the flexural capacity of a concrete section. So calculating our strain diagrams, determining our phi factor, right? Checking for a minimum steel, all this stuff. And again, we're kind of glossing over this because we have other videos where we go into detail regarding this. So our flexural capacity then is 1,148 kip foot. We check our one-way shear capacity, right? So this is what we're talking about here with our one-way shear capacity. and we reference our ACI equations to get our capacity. We are not including steel reinforcement as part of the shear capacity, just the concrete. Gives us 372 kips, and with including our fee factor, brings that down to about 280 kips. And then we can go into our two-way shear capacity, right? It's a little bit more involved here for this one. We got to calculate our pedestal ratio, our punching shear perimeter, and then we have 3 separate equations that we check for punching shear or two-way shear, and then we take the minimum of those, which comes out to be 645 kips. And again, not including any steel reinforcement. So our total then design shear strength is 483 kips, which is our controlling design check for this foundation. So that is the CalcBook Foundation Design module. We hope you enjoyed it, and we'll see you next time.